Hello everyone, welcome to this lecture series. Uh, Today we are going to talk about power series and convergence. So far we have talked about infinite series of numbers. Now we are going to work with an infinite series of powers of some variable. Okay, and so we can call such infinite series as power series, and the series will look like an infinite polynomial. Okay, so we'll talk about what is the definition of power series, and then what is the convergence of it, what is radius of convergence, and then we can extend to define the Taylor and Maclaurin series, and so on. Okay, so let us begin with the formal definition of power series. So, a power series about x is equal to 0 is a series of the form this summation a n x power n, where index n varies from 0 to infinity. Okay, so if we expand this, so it will look like an infinite polynomial as a naught plus a1 times x plus a2 times x square plus a3 times x cube plus so on plus an times x power n plus so on. Okay, so here x is a uh, variable, and a naught, a1, a2, a3, so on, an. So these are constants. Okay, and this is written in powers of x, so that's why we call it a power series about the origin, about x is equal to 0. So if we calculate the power series about any other point, say x is equal to a or x is equal to c, so a power series about x is equal to c will be in powers of x minus c. Okay, so it is of the form summation an x minus c whole power n, where index n varies from 0 to infinity. Okay, so now this infinite polynomial is in powers of x minus c. Okay, so that means we are trying to find out a power series about this point x is equal to c, and these ai's are constants. Okay, and c is the center of this series about which this infinite series is written. So first question that arises is whether this infinite series converges or not, and if converges, then for what value of x this infinite series will converge. Okay, so first we will take one theorem. That theorem is about the convergence for the power series. So if the power series is given by this, okay, a n x power n for n 0 to infinity, that means about origin. Okay, similarly we can say, we can use x minus d power n, okay, about any point. Okay, so if the power series converges at a point x is equal to c, where c is a non-zero point, then it converges absolutely for all x with uh, this interval, the absolute value of x less than absolute value of c. Okay, and if the series diverges at any point d, then it diverges for all x with this, the absolute value of x greater than absolute value of d. Okay, so this is the theorem for convergence, and we'll okay, just prove this one first. That suppose that the series is convergent at this point x is equal to c. So if we put x is equal to c here, so this series a n c power n is a convergent series. Okay, and we know by nth term test that uh, if the series is convergent, then limit n tends to infinity on the nth term must be 0. Okay, so limit n tends to infinity, a n c power n must be equal to 0. Okay, by nth term test, because if this limit is non-zero, then the series will be divergent, but it is given convergent, so this must be 0. Okay, and uh, so there exists an integer capital N such that the absolute value of a n c power n must be less than 1 for all n greater than some integer capital N. Okay, and so that we can rewrite this as and calculate a n in terms of c n as absolute value of a n is less than 1 by absolute value of c power n for all n greater than equal to capital N. Okay, so if we multiply both sides of this with uh, x power n, the absolute value of x power n, okay, then we can rewrite this last expression as absolute value of n into absolute value of x power n less than absolute value of x power n over absolute value of c power n. For all n greater than n, this is true. Okay, and if this uh, right side of the inequality, this absolute value of x by c, if it is less than 1, then by geometric series this right hand side series will be convergent. Okay, so if the absolute value of x by c is less than 1, then this series, which is a geometric series, is a convergent series. Okay, because this r is less than 1 modulus r. Okay, and because uh, this absolute value of a n times absolute value of x power n is less than this. Okay, so by comparison test, the series of this a n x power n will be convergent. Okay, so by comparison test this holds, and so we have the proof of first part that the original series a n x power n will converge absolutely because its absolute series is convergent. Okay, and it converges for this condition. Okay, that modulus of x is less than absolute value of c. Okay, so that's the condition. Okay, so if that means that if the power series is convergent at any point, any non-zero point, then it converges in the interval from minus c to plus c. Okay, the second part says that if the series is divergent at some point d, then it diverges for all x such that modulus of x is greater than modulus of d. Okay, so we'll prove that part now. Suppose that the series a n x power n diverges at the point x is equal to d. Okay, so we'll prove that it diverges for all x such that the absolute values of x are greater than absolute values of d. Okay, so let uh, x be a number with this condition that the absolute value of x is greater than absolute value of d, and also assume that the series converges at this x. Okay, so if the series converges at this x, then part 1 says that the series must converge for all x from minus x to this capital X, and because d is less than this, so it must converge at d. Okay, but that is not true because it is divergent at d. So that means our assumption that if x is a number bigger than this and it converges is not true. That means if x is a number bigger than this, then it must diverge at these numbers. Okay, so that means the series diverges for all x with this condition. Okay, so that's uh, the theorem. Okay, so that means we have seen that the series can converge in an interval. Okay, and if c is infinite, so the series can converge at all points. Okay, and if c is 0, then the series will converge only at one point. So there are three possibilities that series can converge at a point which is the center, or the series can converge in an interval, or the series can converge for all values of x. Okay, and from there we can define or calculate the what we call the radius of convergence of a power series. So the convergence of this series a n x minus c power n, where n varies from 0 to infinity, is described by one of the three cases, and those three cases depend upon whether this series converges at a single point or converges for all values of x or converges in a interval. Okay, so the first case, say there is a positive number r such that the series diverges for all x with absolute value of x minus c bigger than r, but converges absolutely for all x with absolute value of x minus c less than r. Okay, so that means the series converges absolutely in uh, an interval. You can easily rewrite this as c minus r to c plus r. Okay, and the series may or may not converge at either of the endpoints. Endpoints are x is equal to c minus r and x is equal to c plus r. Okay, so that means if we calculate the convergence of this power series, and if it gives the interval in which it is converging, and outside that interval it is diverging, so the endpoints of this interval, on those points we need to check separately whether the series is converging or not. And it is possible that the series may not converge at any of the endpoints, or it may converge at both the endpoints, or it may converge at the lower endpoint and not upper, or it may do not converge at lower and may converge at upper. Okay, so anything is possible at endpoints also. Okay, the second possibility is that the series converges for all x. Okay, so in that case this r will be infinite. Okay, and the third possibility is that the series only converges at the center at x is equal to c. Okay, so the series converges at x is equal to c and diverges everywhere else, so this r is equal to 0 in that case. Okay, here this r is called the radius of convergence of the power series, and the interval of radius r centered at x is equal to c is called the interval of convergence. Okay, so either you will get the convergence in an interval like this. Okay, or you can get that the series converges for every x. In that case the radius of convergence will be infinite. Or you can get that the series converges only at the center x is equal to c, about which the power series is written. In that case the radius of convergence is 0. Okay, and the interval of convergence may be open, closed, or half open depending upon the particular series. Okay, and because we have to calculate the convergence and divergence at the endpoints separately, so and depending upon how they behave, the interval may be open, closed, or half open, and so on. Okay, uh, so how to now we have seen that uh, the convergence of power series can be of three types. That means it can be in an interval or for every x or at a point. But now the question is that how to find out this interval of convergence, or how to uh, find out this value of r, or how to calculate the convergence for this power series. Okay, so how to test the power series for convergence? So the idea is that you can use the ratio test or root test to find the interval where the series converges absolutely. Okay, and ordinarily this is an open interval. Okay, more absolute value of x minus c is less than r, or this can be written as an interval that x lies between c minus r to c plus r. And because if you found this as a uh, infinite interval, then there is no need to calculate anything on the boundary. Or if you found that r is 0, then it is converging only at a one point x is equal to c, then again there is no boundary point to be checked. But if you found that r is a finite and it's a finite interval, then we also need to calculate the convergence at the boundary point. That means that x is equal to c minus r and at x is equal to c plus r separately. Okay, and so for uh, if the interval of absolute convergence is finite, test for convergence or divergence at each endpoint, and for that one can use like comparison test or integral test or the alternating series test depending upon what series is available in hand. Okay. uh, One third important point to note is that if the interval of absolute convergence is C minus R to C plus R, then the series is definitely going to diverge outside. That means for all x satisfying this x minus C absolute greater than R, and uh, it does not even have a conditional convergence for these points x which are outside this interval. Okay. Because the nth term does not approach 0 for those values of x which satisfies this. Okay. So idea is simple now, that if you are given an infinite power series, so for absolute convergence to check, find out the interval, we can use ratio root test, and then at end point you can use any of the other test. Okay. Say for example, say for what values of x do the power series converge, where power series is given as minus 1 raised to power n minus 1 x power n by n varies from 1 to infinity. Okay, and if you expand this into infinite series power series, then it can be written as x minus x squared by 2 plus x cubed by 3 minus x 4 by 4 plus 1. Okay, so first step is to calculate or find the points x or the interval x in which this power series is converging absolutely. Okay, so for this case, let us apply the ratio test to the series of absolute values, okay, which is this series of absolute x power n over n. And to apply ratio test, if this is your an, then you have to write an plus 1 and calculate the ratio n plus 1 by an and see what happens when n becomes large. Okay, so if we calculate this un plus 1 by un here, then this is un plus 1 and this is divided by un, so it reverses, and so we can rewrite it as n over n plus 1 into absolute value of x. So when n goes large, this tends to absolute value of x, and we know by ratio test that this series will be convergent if this when n goes large, this value is uh, less than 1. Okay, so that means the absolute value of x must be less than 1 for this series to converge absolutely. Okay, so the series converges absolutely for when this absolute value of x is less than 1, and this immediately says that it diverges for all x satisfying that absolute value of x is greater than 1. Okay, and we also need to check at the endpoints. Okay, so minus 1 to 1 is the interval, so for x is equal to 1 what happens, and x is equal to minus 1 what happens. Okay, so if I take x is equal to plus 1, then you can see that if I plug x as plus 1, so it will be 1 minus half plus 1 by 3 minus 1 by 4 and plus so on. Okay, and we know that that's an alternate harmonic series which is convergent. Okay, so at x is equal to plus 1, the series is this, which is alternating harmonic series and which is convergent. And if x is minus 1, so if you plug x as minus 1, then you can see that if I take negative sign outside, then it is a divergent harmonic series. Okay, so x is equal to minus 1 is divergent harmonic series. So that means the series converges for all x satisfying absolute value x less than 1 and converges at x is equal to 1, but diverge at x is equal to minus 1 and other values of x. So we can write that the series converges for minus 1 less than x less than equal to 1 and diverges everywhere else. So this is our interval of convergence, minus 1 less than x less than equal to 1, and the radius of convergence is 1, absolute value of x is less than 1, which is r. Okay, so r is 1. Okay, say we take one more example here. Say for what values of x do the power series converge. Okay, say given power series is n factorial times x power n varies from 0 to infinity. So if we plug n values 0, 1, 2, so on, so this can be written as infinite power series as 1 plus x plus 2x square plus 3 factorial x cube plus 4 factorial x4 plus so on infinite. So again, to solve this, let us apply the ratio test to the series. This is our n factorial x power n, so an plus 1 will be n plus 1 factorial into x power n plus 1. Okay, calculate the ratio of an plus 1 by n. Okay, so writing un by un. So we have un plus 1 divided by un. Here we should have n factorial. Okay, not n but n factorial this term. And n plus 1 factorial can be written as n plus 1 into n factorial, so n factorial will cancel out and we'll have n plus 1 into absolute value of x, because the x power n will cancel out. And when n becomes large, then this product will become infinite, uh, except when the absolute value of x is 0. That means except when x is 0. Okay, so this goes to infinity unless x is 0. Okay, so for any non-zero x value this goes infinite. That means that this series is divergent for every x except for x is equal to 0. Okay, so that means this series is convergent only at the center x is equal to 0. Okay, so this was about the power series and its convergence. Now next is the Taylor series and Maclaurin series, which is representing functions with a power series. Okay, so the functions that are infinitely differentiable generates power series, and we call that as a Taylor series. Okay, so let, if you are given a function fx be a function with derivatives of all orders throughout some interval containing a as an interior point, then the Taylor series generated by this function fx at x is equal to a, that means in powers of x minus a, okay, is given by this infinite power series, which is kth derivative of function at the a over k factorial x minus a whole power k. Okay, so here f superscript in brackets k means that we are taking kth derivative of the function and calculating that kth derivative at the point a. Okay, so if we put k 0, 1, 2, so on, so this can be written as an infinite power series as function value at a plus when k is 1, okay, it will be f1. Okay, that means the first derivative at the point a into x minus a division by 1 factorial, which is 1, plus when k is 2, so it will be f bracket 2 at a, that means second derivative function at a. Okay, so that's second derivative function at a by 2 factorial x minus a whole square. Okay, 2 factorial x minus a whole square plus so on, plus nth derivative of function at the point a over n factorial times x minus a whole power n plus so on. Okay, so this is the Taylor series representation of the function fx about the point x is equal to a. Okay, and if we calculate this series about origin about x is equal to 0, that means if we put a as 0 and rewrite this, then that series is known as the Maclaurin series. Okay, so Maclaurin series of function is the Taylor series generated by this function about the origin about x is equal to 0. Okay, so it is like infinite series with function kth derivative at 0 over k factorial into x minus 0 power k, so simply x power k. Okay, that means we are going to get a series in powers of x. Okay, and so if you expand this, so it will be function value at origin plus first derivative of function at 0 into x plus second derivative of function at 0 divided by 2 factorial into x square plus so on, the function nth derivative at 0 by n factorial times x power n plus so on. Okay. So this is the infinite Taylor series representation for a function when function has derivatives of all order throughout some interval containing the point about which the infinite series is written. Okay, and if we want to write the corresponding polynomial from this Taylor series, so we can write the Taylor polynomial of order n, and we write it as Pnx. It is nothing but the truncated part of this series. Okay, so if we want to just write the polynomial for order n, means the up to the nth derivative all the terms of this infinite series. Okay, and so truncating at the nth derivative term, and so if we want to say write the first order Taylor polynomial, so that means the up to first derivative terms f of a plus f dash a x minus a. Okay, so these two terms. If we want to write the second order polynomial, so that means up to second derivative, so f of a plus f dash a into x minus a plus second derivative at a over 2 factorial x minus a square. Okay, so first three terms and so on. Okay, so we can write the Taylor polynomial of any order, first, second, third, and so on, from by truncating the infinite series. Okay, and you can see that if uh, you just calculate the first order polynomial from the Taylor series, then it is f of a plus f dash a into x minus a, and from calculus we know that this is nothing but the linearization of the function. Okay, so that means uh, we can write or we can approximate the function by its linear. Okay, that we have already did in calculus, and similarly from here from the Taylor polynomial we can not just approximate by linear polynomial, we can approximate by any order polynomial. So we can find a function's quadratic approximation by approximating this function by up to second order polynomial, or we can approximate this function up to any nth order polynomial and so on. Okay, now two questions that arises here is how accurately these Taylor polynomials approximates the function. Okay, and the second question is that for what values of x can we normally expect this Taylor series to converge to its generating function, which is fx. Okay, so from fx we have written this series, but does the series converge and converge back to this function or not? Okay, so these are two important questions. Okay, so we'll talk about the convergence of this and whether it converges back to function. Before that, we just take one example to show you how, if you are given a function, how you can calculate this Taylor series or the Maclaurin series. Okay, so let us take this one simple example, that find the Taylor series and the Taylor polynomials generated by function fx is equal to e power x at x is equal to 0. So it is about origin, so this Taylor series will be same as Maclaurin series, and to calculate Taylor series we need the derivatives of the function. So first derivative, second derivative, third derivative, and so on, nth derivative of this e power x at x0. Okay, and we know that exponential derivatives remain exponential, so it is a simple example here. So functions nth derivative at x will be e power x, so that means all derivatives of this function, because it remains e power x, and at x is equal to 0 we can calculate all derivative values. E power 0 is 1, and this is true for every n 0 1 2 so on. And the Taylor series generated by function at x is equal to 0 is given by this formula. Okay, f of 0 plus f dash 0 times x plus f second derivative 0 by 2 factorial x square plus so on. Okay, so before we substitute, if we have to calculate for any other point x is equal to a, Then this nth derivative, again we can calculate fn at x is equal to a, okay, so it will be like e power a, and this formula can be written as fa plus f dash a into x minus a, okay, f second derivative a into x minus a square plus 1, okay. So we can calculate not just at origin but about any point x is equal to constant, okay. Now for this particular case, if we substitute f0, f dash 0, f second derivative 0, the values fn 0 is 1, okay, so all these values are 1. So this can be written as infinite series 1 plus x square by 2 factorial plus so on plus xn by n factorial plus so on, and this can be written in summation form as x power k by k factorial k0 to infinity, okay. So this is the infinite power series representation for this function, okay. And the corresponding Taylor polynomial is nothing but the polynomial of order n truncated polynomial from this infinite series, okay. So the Taylor polynomial of order n at x0 is written as pnx, which is 1 plus x square by 2 factorial plus so on xn by n factorial, okay. So up to nth derivative term, okay, from this infinite series. So this is how you can calculate the Taylor series and the Taylor polynomials, okay. So one question is clear, that if given a function, you can if it is differentiable for all orders, then you can write the corresponding series, okay. Now two questions that I said is whether this uh, Taylor polynomial approximates accurately this function, or does this infinite series converges, and if it converges, does it converges back to this function for some values of x or all values of x. So can we write it equal to the series equal to e power x or not, okay. So all these questions are answered by the convergence of Taylor series and using the Taylor's formula, okay. So if function has derivatives of all orders in an open interval I containing a, then for each positive integer and for each x in I, we can write fx as the Taylor polynomial plus a remainder, okay. So this f of a plus f dash a x minus a plus f second derivative a over 2 factorial x minus a square plus so on fn a over n factorial x minus a power n, up to here it is nothing but pnx, the Taylor polynomial of order n, plus the rnx, which is called the remainder, okay. So function can be written as a Taylor polynomial of order n plus the remainder, where this remainder is given by the next term of this Taylor polynomial, which is n plus first derivative over n plus 1 factorial x minus c power n plus 1, okay. So n plus first derivative n plus 1 factorial x minus a power n plus 1, where but the derivative is calculated at a point c, where c is some point between a and x, okay. And this Rnx, as I said, is called the remainder of order n, or it is called the error term for the approximation of function by the polynomial, okay. So this function is Taylor polynomial plus Rnx, pnx plus Rnx. So this Rnx is nothing but the error term if we approximate function by the Taylor polynomial, okay. And if when n becomes large, if this Rnx goes to 0, okay, if Rnx goes to 0 as n goes large for all x in the interval, okay, we say that Taylor series generated by the function at x is equal to a converges back to function, okay. So then this series, which will become infinite series, will converge back to this function, and we can write the infinite series equal to the function, okay. So for example, in the previous case, if I write that Taylor polynomial plus the uh, error Rnx, and if limit n tends to infinity Rnx is 0, then I can write that infinite series equal to e power x in the previous example, okay. So So we can check whether this series will converge back to fx by using this method. And so how much is the error? Can we estimate this error? That is another question arising from here. So there is one result which is the estimation of this error, and which is known as the remainder estimation theorem, and it says that if there is a positive constant m such that the n plus first derivative of function is bounded by this number m for all t between x and a inclusive, that means t can take a value of x as well as a, then the remainder term Rnx in Taylor's theorem satisfies this inequality, that the absolute value of the remainder is bounded above by m times absolute value of x minus a power n plus 1 over n plus 1 factorial. Okay, if this inequality on the remainder holds for every n and the other conditions of Taylor theorem are satisfied by the function, then the series converges to fx. Okay, and then the infinite Taylor series, which is written from the function, converges back to the function. Okay, so this is an important result in the sense that we can calculate the error at any point x in the interval of convergence. Okay, so to close this, I'll just show with our previous example, show that the Taylor series generated by the function fx is equal to e power x at x is equal to 0 converges to fx for every real value of x. Okay, so that means if we write the Taylor series for exponential function, then that series converges back to e power x. That means we can write series equal to e power x. Okay, so this we just did in the previous example, that if you have a function e power x, then about origin its Taylor series can be written as this 1 plus x square by 2 factorial plus so on x power n by n factorial plus so on. Okay, now we have to show that this series can be written as equal to e power x. It converges back to this exponential. Okay, to prove this, let this function can be approximated by the Taylor polynomial plus remainder. Okay, so we write the Taylor formula, which says that the function fx, which is e power x, can be written as Taylor polynomial of order n plus the remainder Rnx, where Rnx is the next term, which is f of n plus 1 at c into x power n plus 1 by n plus 1 factorial. Okay, so Rnx is x power n plus 1 over n plus 1 factorial into n plus first derivative at some point c, where c lies between uh, a and x, so 0 and x. Okay, and because n plus first derivative of x is also e power x, so at c it is simply e power c, so we get here e power c by n plus 1 factorial x power n plus 1. Okay, so now we just need to show that this goes to 0 when n goes large. Okay, so since exponential functions are increasing functions of x, and so because c lies between 0 and x, so e power c must lie between e power 0 and e power x, so e power c lies between e power 0, which is 1, and e power x. Okay, now if x is positive quantity, then 1 will be less than e power c will be less than e power x, so e power c will be less than e power x. And if x is a negative or 0, then e power x will be less than e power c, and that will be less than e power 0, is that means 1. Okay, because x is negative means c will be between x and 0, x negative means c will be negative, so e power x will be less than e power c will be less than 1. Okay, so based on the two conditions, we can rewrite Rnx. Okay, so the absolute value of Rnx will be less than equal to this, when x is negative, because when x is negative or 0, then e power c is less than 1, as we just said. Okay, so e power c will become 1, so it will be simply less than this. And if x is positive, then e power c will be less than e power x. Okay, so the Rnx is bounded above by this. Okay, and so if I take n tends to infinity, in either case, limit n tends to infinity on x power n plus 1 by n plus 1 factorial is 0, so it immediately gives me that limit n tends to infinity Rnx is 0. And by definition, this series converges to e power x, and we can write e power x as the infinite series. Okay, so this is our Taylor series and its convergence. Okay, so we close this topic here, and in this next lecture we'll start with the concept of integral calculus. Till then, have a very good day.